Hi, and welcome to 9.5 Conservation of Momentum, Recoil, and Explosions. In this lesson, students will be able to use the law of conservation of momentum to fully describe the motion of objects exploding and or recoiling. So this recoiling occurs when two objects are initially together and then separated. So it looks like this initially, and then there's some kind of explosion that happens, and then they separate, and they have momentums moving in opposite directions. So it says, how would you rewrite the conservation of momentum formula in this situation? Ooh, pause the video and think back to that formula. How would you write it down? Maybe this helps. Is the combined masses in the beginning, and then the masses separate. So you might want to have a combined formula here, a combined expression there, and then V1F plus V2F, right? So it looks something like that. So a classic example of a recoil or explosion problem is a cannonball being fired from a cannon or a bullet being fired from a gun. In both cases, you have a more massive thing that's holding a less massive thing. So the red thing could be like the bullet or the cannonball, and the blue thing could be the big massive cannon or the gun itself. So initially they're together, then there's an explosion that sends the projectile flying. What also happens is you get what's called recoil, and either the cannon moves backward or the gun gets moved backward into the person's hand. So there's some recoil there. If the objects are initially at rest, which will have the greatest final momentum? Is this a greater momentum or will this have a greater momentum? And then which will have the greatest final velocity? It's like a critical thinking question. All right, so pause the video and think about it, and then I'll give the answer here. So if they're initially at rest, what is the total momentum of the system? The total momentum of the system is 0 kilogram meters per second. And the final momentum of the system, therefore, has to also be 0 kilogram meters per second. So that means that this momentum, P1F, plus this momentum, P2F, when you add them together, they have to equal 0 because the total momentum has to remain the same. It's the conservation of momentum. So even though this one has some momentum to the left, this one has some momentum to the right, they're equal in magnitude and opposite in direction. So to answer the first part, which has the greatest final momentum? That's a trick question. They have the same final momentum, but they're just pointing in opposite directions. Now, which will have the greatest final velocity? Well, the cannon, the big heavy cannon, be traveling at the same speed as the cannonball? We know that it won't be because we have the mass times the velocity here and the mass times the velocity here. This cannon is more massive, so it needs less velocity in order to have the same magnitude of momentum. This bullet is not massive at all, therefore it needs a much greater velocity to have, again, the same momentum, just in opposite directions. So which one has the greatest final velocity? You probably can picture it in your mind, but the bullet or the cannonball will be moving faster, but since it's less massive, it has the same momentum. So that's the idea there. So we're going to add another equation to our list here. All right, so this is what we had initially, where the two separate objects, they bounce off each other for totally elastic collisions, but now they're going to start together. So we could have m1 plus m2 times the same velocity, and 9 times out of 10 for this class, that velocity is going to be 0. Like the cannon is going to be at rest. It's not going to be moving. You could have some initial velocity where they're both moving together, and then there's an explosion, and you could figure out what the final velocity is going to be, because in that case, there would be some initial momentum. But most of the time, the velocity is 0, so the initial momentum and the total momentum for the system is also 0. But technically, this is what the equation looks like for that. And then since we know that the total momentum is 0, what does that mean? we can subtract to one side and we say, okay, this is what we were talking about before, but mathematically they have the same, they're equal to each other, the same momentum, but in opposite directions, right? If the um, initial velocity was zero, you could do that. But if it's not zero, this is our formula that we use. So there's a couple videos in the extension folder that you could check out for Recoil. And then a couple videos about explosions. All right, this one's really cool. Talks about classic physics experiment with these balls being dropped, and then what happens. What do you think will happen to this ping pong ball? Crazy stuff. And then the explosions with a grenade, all the shrapnel in there. It's kind of interesting. So if you add the momentum of each little piece of shrapnel, they all, when you add it all together, it equals the initial momentum of the grenade as a whole, which is kind of cool. So let's do an example. It says an 80-kilogram clown is fired from a 400-kilogram cannon. If the clown's speed is 20 meters per second after firing, what is the recoil speed of the cannon? So they're saying that this clown is moving at 20 meters per second. What is it? The cannon's going to be moving backward. We want to know how fast. So we'll write our givens down. We'll call M1 is 80 kilograms. That means the cannon is M2, and that's 400 kilograms. And it says, it doesn't say specifically, but we can assume that the initial velocity is 0 meters per second because normally cannons are just at rest. So that's kind of an assumption that you have to make. It says if the clown's speed is 20 meters per second after firing, so V1F is 20 meters per second because we made the clown M1, so it's V1F. What is the recoil speed of the cannon? V2F. So it still boils down to the same principle that the initial momentum of the system has to be equal to the final momentum of the system. And you could write it the way we had, so M1 plus M2 times their initial velocity together, because the cannon and the clown start off together. And then after the explosion, they separate, so M1 V1F plus M2 V2F, okay? But we know that VI is zero. So the initial momentum of the system is 0 kilogram meters per second. And the final momentum of the system is also equal to zero when you add these two quantities together. So this is 80 kilograms times 20 meters per second plus 400 kilograms. And we're going to assume that this is going to be a negative number because when you add them together, we better get zero. But we'll just plug in V2F for now and let the math tell us that it's negative. Let's see when we solve, is it going to be a negative number? So we get 0 is equal to 1600. So the clown has a momentum of 1600 kilogram meters per second. And then we want to know what is the final velocity or the recoil velocity of the cannon. So you subtract then 1600, right? You get, oh, negative 1600. This is looking good for our prediction that we should get a negative number for the final velocity because it should be moving in the opposite direction. And you divide and you get V2F is equal to negative 4 meters per second. So if I was going to draw a picture, all right, the clown is moving this way with a high velocity, 20 meters per second, and the cannon is not moving as fast. It's only 4 meters per second in the opposite direction, but the momentum of each is the same, equal in magnitude, opposite in direction. All right, now for this practice problem, it's not a cannon, it's not a gun, but you could still have this same concept in a different situation where anytime two things are together and then they separate, you can use this same concept. So here it says a 90 kilogram skater and a 70 kilogram skater are both skating together with a velocity of 3 meters per second east. So they're like embracing each other, they're moving together at 3 meters per second east, okay? So this is, not only is it not a cannon gun problem, It's two ice skaters. But now we do have the situation where your initial velocity is not zero. You do have some initial momentum for the system. So we can use that equation that we put in before. The two skaters push each other apart. So they're together and then they separate. The 70 kilogram skater moves with a velocity of 10 meters per second east. What is the velocity of the 90 kilogram skater? Are they also going to continue moving to the east, or did they push each other enough? Did the one skater exert an impulse on the other skater with enough magnitude to start making them move in the opposite direction? We don't know yet, but we could do the calculation. Or actually, I want you to do the calculation and see. You can make a prediction first. Do you think the 90 kilogram skater is going to move to the east or west? And then do the calculation and try it out for yourself. All right, so I'm going to make the 90 kilogram skater M1, and M2 is the 70 kilogram skater, and they're both moving together with an initial velocity of 3 meters per second. So they're like on their little skates here, and they're moving as a unit 3 meters per second to the right, to the east. Okay, positive. The two skaters push each other apart. So then, all right, we know this velocity, they get faster. Actually, I'll make the arrow more to the right, 10 meters per second. We don't know what the final velocity of this one is, though. We'll call this 1. This is 1, 2, 1, 2. All right, so we want to know what that final velocity is after the push. Actually, I think I messed up my subscript. So let's see. The 70 kilogram skater, which we made M2, is moving now with the final velocity V2F, because that's the 70 kilogram skater, 10 meters per second to the east. What is the, oh yeah, perfect. That's what I did. Nice. Okay, great. I'm going to erase this diagram so we can do some math. It's still the same concept, the law of conservation of momentum. The total momentum initially has to be equal to the total momentum after they separate. And initially, they are moving together. M1 and M2 are moving together with the same initial velocity, but then they separate out. And we want to know what the final velocity of M1F is. Oh my gosh, M2 V2F. Okay, so you plug in your numbers, and this is how it's different, because before we were just like, oh, it's at rest, so VI is 0. But no, no, no. Now there is some initial velocity. There is some initial momentum for the system. So 90 plus 70 kilograms times the 3 meters per second they're traveling initially at that rate. And then 90, we don't know what the final velocity is, but the math will tell us whether it's going east or west if we get a positive or negative number. This is 70 times positive 10 because it says east. Okay, good. So the initial momentum for the system is 480 kilogram meters per second east. That's the whole system. And then the second skater has 700 kilogram meter per second east. So is that enough information now to make a prediction of what direction the velocity is going to go in? What do you think? Well, let's continue solving. The final velocity is negative 2.4 repeating meters per second. So in our diagram, the person is moving to the west because we got V1F is equal to negative 2.4 meters per second. Not as fast, so they're really just like launching the second person away at a fast velocity, all right? But they end up pushing themselves back a little bit too as they exert that force on them. Pretty cool stuff. Anyway, that's about it. Thanks for watching and have a great day.